Welcome to the last section of the optimization lecture. To start, let's just talk a little bit about how computers calculate. Surprisingly, they do not calculate as well as you and I might using actual mathematics. They do not have the memory span, I guess is the way to put it, but you'll see why in a moment. Numbers are stored specifically as two components, an abscissa and exponent, and if we consider there's a certain number of digits available to the abscissa. So let's think of a 16-digit abscissa. Then we might have a number that is 1 point, and the point is always there, 1 point. And we've got, I just counted out 16, so 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there is 16 places. And perhaps our number is going to be that number times 10 to the negative 7. That's our exponent up there. When the computer adds or subtracts, it requires the same exponent. So here's a problem. Let's suppose we want to add these two numbers. What is the computer going to do? The computer is going to move them all to a times 10 to the 0. So it's going to convert this to a 10 to the 0. How does it do so? It does so by moving this decimal place this way. But it can only preserve 16 spaces. So every space it goes this way, it has to drop off one of these. So it drops off 1, 2, 3, 4, 5, 6, 7 spaces, and now we get this number, which means we lost that information when we added. Now this may not seem like much, but if you have a large database and you are going to add them and you do not align the abscissas up in a particular order so that they do not drop information, then you can end up losing data and be imprecise. In fact, you can be quite imprecise depending on how much of these digits you end up losing for how many in the data set. The loss of precision in the operation of matrix inversion, and I mention this specifically because really what can dominate this in our optimization routines is inverting that matrix's second derivatives. The loss of precision is the log 10 of the eigenvalue, is the ratio of the largest eigenvalue to the smallest eigenvalue. Remember seeing that as the condition number. So, if your log 10 of the condition number is greater than 10 to the 15, essentially you will lose everything, because that's the loss of precision. So, this is a problem. Now, in calculating the numeric Hessian, where, again, the numeric Hessian is the difference calculated, it's kind of the numeric derivative of the numeric derivatives. When you calculate the numeric Hessian, you tend to lose approximately 8 places. So in a 16-digit machine, you're losing essentially half of them are gone in terms of precision. So again, this is suggesting that one needs to be careful in the computing of their numbers. And fortunately, this is not something that we can do much about, but computer programmers can organize how they do their calculations to be more or less effective at it. So this is one of the results that we tend to get is a loss of about 8 places in the Hessian. But it's interesting, there are some comparisons out there between software such as Stata and other calculating software, and they will vary in their precision depending on how they organize their matrix manipulations. But here is just one result is an approximate loss in the numeric Hessian. Do we care? Well, it usually works out pretty good without worrying so much about it. But nonetheless, The BFGS algorithm minimizes this problem because the way that it is working on this is it constructs its weight matrix. It's parallel to the Hessian, essentially, slowly as it goes along in its calculations, and it does it in a way that minimizes the loss of precision. So this is one of the benefits of this particular algorithm. And just a brief note is that technically we have to redo all of that in our conversation on base 2 if we were to try to talk to computer scientists. But from our perspective, being outside of the machine language itself, the preceding applies. Okay, so let's go on to one final question. That is, how do we know when we've arrived? Right? I mean, we're basically approximating. We're taking steps up closer and closer to hopefully the top of the hill or the bottom of the valley. How do we know when we arrive? Well, one possibility is to say that the change in the beta is approximately 0, or the change in the function of the beta is approximately 0. So in other words, we may have some like this, and we're saying, well, gee whiz, now that we're calculating our changes, we only need to go almost nothing. Or we look this direction and look at the f as barely changing. It's not a very good criteria, however, because if it's a long, flat slope, you can end up with not being able to identify whether this is the case being near the top or just simply very slow plotting. If f is not quadratic, we might be taking really, really small steps, and essentially we look like we're having very little improvement in our function or beta. Another possibility is we can look at the derivatives. Is the slope approximately 0? So we could technically ask by approximately 0 is to provide some threshold and say, well, is the slope less than that threshold? Alternatively, we can use a combination of the slope or the gradient and the inverse of the negative Hessian and ask that this be very small. This is probably the better of the bunch. And you can set this in Stata will allow you to set this tolerance level. You can set it at some reasonable value, say for example 0.0001. It's reasonable, but you can set it at different levels. And I will talk later at some point about actually how to investigate these convergence rates. But for the moment, we'll go by that. All right, so now how do we check the solutions themselves? Well, one possibility is, what you should do is try different starting values. And this is to try to make sure that you're not, with a complex function, you're not in some local maximum that's nowhere near a global, which you really want. So if this is your function and you start here, you're going to end up with that. So you want to start at a couple of different values so that you can start here and here, and this one will get you to there, and this one will get you up to here. So you want to be able to identify a good starting value, and you may want to check it out by trying a few different values to make sure you converge to the same maximum. You want to evaluate whether the gradient is approximately 0, but of course this depends on the scale. And you want to look at the convergence rate. And the convergence rate, which I will explain in a bit, are predictable. They directly come from the kinds of algorithms. So steepest descent means that it will converge linearly. Each step will just be a linear step. Newton-Raphson will be quadratic in its approach to the maximum, and the quasi-Newtons will be superlinear, which means they will be somewhere in between the two of those. So let's consider a distance from the optimal point, or we could consider it the functional value, the difference in the functional value. Linear convergence means essentially that the magnitude of this difference, how far away you are at each iteration, is just some constant linear component of, or scale of the distance it was before. Quadratic means actually that the next step is actually a function of the square distance, quadratic distance. And so it is actually going faster, converging faster. Superlinear, again, is in between. And when we start using Stata with some results, I will show you how that actually looks in the Stata output. Another thing is to inspect the Hessian matrix, and Stata will report this for you. And you want to see if it's positive definite or if it's negative definite. That would give you a sense as to whether or not you are at the top of a hill or not. You want to ask, is it ill-conditioned? You want to know if the solution is in a flat area. There will be loss of accuracy if it's not. And the quadratic approximation will fail in at least one direction. And if that's the case, the Wald statistics that you use will not be good. We'll explain this later in our maximum likelihood lectures as to why this is the case. But you want to make sure that it's not an ill-conditioned matrix, and you can do this by the simplest way is to look at a condition number. That can it's not foolproof, but it can certainly help out. So how do we solve issues? Well, again, you can rescale the variables. You can respecify the model, as we said before. You can reparameterize, and you can get more data. That's essentially what you have available to you. Or you can start at a different starting point if that's the problem. Different initial values. You can use different optimizing algorithms, as we've talked about a number of them. If the problem is just simply not converging at all, you're getting some kind of bad results in the process, you might want to try different algorithms. So there's a number of strategies which we'll be using during the course of this class, and I will go over those specifically as we get to them. Another thing to look at is to profile the objective function and determine if it is reasonably quadratic towards its optimum. This is going to help you understand whether or not you can use the statistics such as the Wald statistic, which presumes that it is in fact quadratic. So in order to do this, let's say that f is our objective function. It has two parameters in it. And we want to profile across this particular parameter. So that means that we want to have some values for that parameter and make it vary. So we're going to vary alpha here. This is a parameter we're going to vary now. We're going to vary it from some lower value all the way up to some upper value. Typically, we will center it on the estimated values so that we will have some range of values here from alpha L to alpha U centered on our estimate. And then we will look at our betas as estimates of this profiled equation. It could be called, if it's a likelihood function, be profiled likelihood. And we are looking at getting the beta values that maximize our function for each of the given values in this range up here. And then we can plot each of those alphas with this function that we got, having the alpha that we put in there and then the estimated maximum associated with the beta, and plot this function. And what we're looking for is that at the top here, near the alpha hat, that this is quadratic. But is it? Well, here are two ways of checking this. You can calculate this equation if you're doing nonlinear least squares, or you can calculate this equation if you're doing maximum likelihood. Once you calculate that, some value of tau of alpha, if you plot the tau of alpha with respect to alpha, you should get a straight line. So this plot will come in helpful. You could also create another variable, which is the alphas that in that alpha low to alpha high, your whole set of ones that you had picked. You can create a function of each of those as its difference from the estimate divided by the standard error of the estimate, and then plot these functions. The advantage of this one is not only is it a straight line, but it should have a slope of 1 and an intercept of 0, if in fact it's quadratic. However, and this is important, this function is think of it as if the function can be expressed in some sense of x transpose mx, then for any slice defined by a vector u in any direction, this holds. In other words, when you're at the top, in some fashion where it is quadratic all the way around, then it's quadratic no matter which way you look at this. This becomes quadratic, just simply the direction. And the function is essentially quadratic along a unit vector that points in whatever direction you're looking at. So which basically what this means is that you can look at a slice along each of the betas. So you can take a vector essentially that looks at the first component, the second component, the alpha, the beta, beta 1, beta 2, beta 3, and look along that dimension. This is easy to do in Stata, at least with maximum likelihood, particularly because you can plot, ML plot. I believe that's the command to do this. I may have not forgotten that, but I believe that's the command to do it. And Stata will actually plot the likelihood function along a particular parameter value. And you can look and see if it is quadratic, or you can use equations above it, calculate points along these values, and consider if it is linear in those transformations we used above. Some other issues in terms of problems can be if the solutions are on the boundaries. If that's the case, then Stata will not be able to find them in their usual methods because they are typically looking at interior points because they're looking for the usual maximum or the usual minimum that we consider on the interior of a space. Our concern about global solutions, as I said before, we can look at multiple starting points, and that's about the only way to really consider complex equations, and consequently it can be very difficult to know if you're at a global solution if the parameter space is very choppy. You would have to have so many different starting points, and then you wouldn't know if the starting points themselves, there wasn't something in the middle that you were missing. So this is a smart thing to do, but if it is a very complex, jagged type of a parameter space, then it's unclear whether you're going to get anywhere just because you have a few starting points. Then you could default to something, as I said before, simulated in annealing genetic programming. They have their whole other world of ways of dealing with this. And that will be the end of this lecture, both the session and the lecture on optimization.